Hello everyone, I would like to welcome you back to our EpiStats channel. Today's lecture is on specificity. In essence, specificity is the ability of a test to identify individuals who do not have the condition of interest. Or in other words, if the test has high specificity, then a person without the condition will most likely test negative, and those cases are considered true negatives. However, sometimes patients who do not have the condition still test positive, and that is called a false positive. So the test says they have it, but they really don't. Unfortunately, that happens because no test has perfect specificity. But the higher the proportion of true negatives, then the higher the specificity of the test. And conversely, the higher the proportion of false positives, then the lower the specificity. If a test is being used to make a definitive diagnosis, then it is most likely associated with a low proportion of false positives. That is, a test with high specificity mostly tells patients without the condition that they do not have it. It is a low false positive rate that makes highly specific tests useful for diagnostic purposes. And that makes sense because you would not want a diagnostic test to incorrectly tell patients that they have the condition when in fact they do not. A middle-aged woman presents to the emergency department with an acute onset of dyspnea occurring one day following an overnight flight. Her only other complaint is a painful and swollen right thigh. With appropriate therapy underway, initial studies returned non-conclusive. D-dimers are elevated and the plain chest X-ray is normal. A pulmonary angiography is ordered to confirm the diagnosis of a pulmonary embolism. This rather basic vignette shows the ability of a very specific test to help to confirm a diagnosis. Another example would be the double-stranded DNA antibody test for diagnosing systemic lupus erythematosus. However, it must be noted that if the prevalence of the condition is low and the specificity of the test is not sufficiently high, then the test may produce more false positives than true positives. That is, most patients with a positive test would not actually have the condition. This issue will be discussed more thoroughly in another lecture. While specific tests can reliably identify individuals without a condition, they are not necessarily good at identifying individuals with the condition. Now, it is true that with a highly specific test, a positive result means the condition is very likely. However, the problem is that specific tests aren't necessarily good at detecting the condition. For some individuals, the test might say they don't have the condition even though they do. That would be called a false negative. So although highly specific tests can confirm a diagnosis, they may not be able to rule one out. Let us imagine that the red rectangles in this figure represent individuals with the condition of interest, while the white rectangles represent individuals without it. The yellow line is the cutoff point above which a test returns positive. Currently, there are several white boxes above the yellow line. Those white boxes represent false positives, meaning that at this cutoff point, the test lacks specificity. As the threshold for a positive test is moved further away from the norm, then the number of false positives decrease. This makes the specificity of the test very high. However, now there are red boxes below the line, representing false negatives. That is the trade-off that occurs when increasing specificity by moving the cutoff point of the test away from the normal range. Medical tests that use a cutoff range to determine the positivity of a test exhibit this type of inverse relationship between specificity and sensitivity. A teenage boy is sent to a pediatric neurologist because his doctor suspects that he may be experiencing seizures. The boy's development has thus far been normal, and he does not have any particular issues that he would like to talk about. After a short discussion, the neurologist suspects the possibility of juvenile myoclonic epilepsy and obtains consent for an electroencephalographic study. No abnormalities are detected. This is an example of a false negative. While EEG can be very informative, People with epilepsy very often have completely normal readings in between seizures. Other tests that commonly produce false negatives include the anti-double-stranded DNA test for systemic lupus erythematosus and an X-ray of the lumbar spine when looking for sacroiliitis. Now that we got all of that out of the way, let's take a look at that cool-looking calculator.
In order to calculate specificity, there are two values that we need. The first value goes in box D. That is the number of patients without the condition who tested negative for it. The second value goes in box B plus D. That is the total number of patients without the condition. When we have these two values, we can calculate specificity by dividing D by B plus D. Now let's try a basic example. Say there are 190 patients without the condition who tested negative for it, and there are 200 patients in total without the condition. All we have to do is divide 190 by 200 to get the specificity, which is 95%. A more complicated question may not provide you with all the necessary information directly. Rather, you may have to determine the values that go in boxes D and B plus D by analyzing the data provided. Let's say, for example, there are 1,000 patients in a study, and the prevalence of disease in that cohort is 10%. This information tells us that there are 100 patients with the condition and 900 patients without it. If we were also told that there were 50 positive tests in total with a positive predictive value of 80%, then we would have enough information to determine the value that goes in box D. Now we just divide 890 by 900 to get the specificity, which is 99%.
Are you ready to test your knowledge? Let's move on to some questions. An imaginary study is conducted to assess the performance of the temporal artery biopsy in diagnosing giant cell arteritis. There were 556 people involved in the study. 191 had giant cell arteritis and 365 did not. The study found that 7 people with the condition and 321 people without it tested negative. What proportion of people without the condition were correctly identified?
This is a rather straightforward question, and much of the data provided is not required to solve the problem. The two values that we do need are the number of true negatives and the total number of people without the condition. There are 365 people involved in the study without giant cell arteritis, 321 of which tested negative. Now all we have to do is divide the value in box D by the value in box B plus D. In doing so, we find that the answer is A, 321 over 365.
Anthony Martin presents to the clinic with joint pains in his hands. He states that his hands are red and puffy and hard to use in the morning. He also complains of having some weird-looking bumps on his elbows. After obtaining the relevant information from the history and physical examination, Dr. Robinson suspects rheumatoid arthritis and counsels her patient that ordering a cyclic citrullinated peptide antibody test would be appropriate. Mr. Martin consents, but admits that he is a little confused about something. What he would like to know is why people sometimes say that a positive result is a bad thing. Dr. Robinson explains that if an investigation is very specific, then a positive test simply means that the patient probably has the condition. In a hypothetical study, 139 out of 155 positive tests and 446 out of 458 negative tests were correct. Based on this information, what proportion of people without rheumatoid arthritis would Dr. Robinson tell her patient are correctly identified by the test?
For this question, we know that there are 446 true negatives, but we do not know how many people in total do not have the condition. In order to determine that value, we first must calculate the number of false positives. Looking at the positive tests only, we see that 139 out of 155 people actually had the condition. That means that there were 16 false positives. Now we just add the number of false positives to the number of true negatives to find the total number of people without the condition. Finally, by dividing D by B plus D, we get our answer. D, 446 over 462.
Kevin Johnson presents to the clinic with a persistent headache on the left side of his head. The headache worries him because he would rarely get headaches in the past and does not know why they would start now when he is 60 years old. He read on the internet that his symptoms could be due to giant cell arteritis and would like to request a temporal artery biopsy. Dr. Brown acknowledges that while that would be reasonable, she must first take a moment to examine him. As they proceed, Mr. Johnson asks if it is possible to not have the condition even if the tests come back positive. Dr. Brown explains to her patient that although the test is very good at diagnosing giant cell arteritis, a positive result would not absolutely confirm it. Nonetheless, it would suggest that an alternative diagnosis is unlikely. If 99 out of 578 positive tests and 29 out of 611 negative tests are incorrect, what proportion of people without giant cell arteritis are correctly identified?
This question does not provide us with the number of true negatives nor the total number of people without the condition. In order to determine those values, we will enter all the data provided into the Punnett square on the left. There were 578 positive tests, 99 of which were incorrect. That means that there were 479 true positives. There were 611 negative tests, 29 of which were incorrect. That means that there were 582 true negatives. Adding the number of false positives to the number of true negatives, we find that there were 681 people in total without the condition. Thus, the answer is D, 582 or 681.
Specificity is important because it gives you an idea about the significance of a positive test. And it does that by working in reverse. A highly specific test tells you which patients do not have the condition. Because if you can be absolutely certain that a patient without the condition will test negative, then you know that a patient with a positive test must have the condition. Thanks for listening to our lecture on specificity.
We hope you enjoyed it and that we'll see you again soon.